Yeah. Hello. Good morning, good afternoon, and good evening, everyone, depending where you are joining from all over the world. And welcome to the third meeting of the Language Circle 2.0. Today, I have the great pleasure to introduce our speaker, Laura Batterink from Canada, who could not be here in person, unfortunately, but we're still very happy to have you here on Zoom. Before I start introducing her, I have a couple of reminders again for our Zoom audience. So the first piece of information is that this session will be recorded and uploaded on our YouTube channel, so that people who could not attend this meeting can also watch it there. And we hope this is fine with all of you. So if you don't want to be seen online, you can switch off your camera. Otherwise, you're very welcome to turn it on in order to give us all a nice sort of atmosphere as we were, yeah. And the second piece of information that I wanted to tell you is that we had one instance of Zoom trolling in a previous talk at the Language Circle. So to prevent that, now we are limiting the possibility of the audience to interact with the speaker during the presentation. So you're all muted for the moment, but no worries. If you have questions during the talk, you can paste them in the chat, or you can raise your hand after the presentation, and we will have some time for discussion and Q&A, and we will unmute you and give you the possibility to talk. So now, after these first disclaimers, I would like to introduce the speaker of today, Dr. Laura Batterink. Laura Batterink obtained her PhD in cognitive neuroscience in 2012 at the University of Oregon with a dissertation on the implicit and explicit neural mechanisms supporting language processing, supervised by Dr. Helen Neville. From 2013 to 2018, she was a postdoctoral fellow in the Department of Psychology at the Northwestern University, Canada, working with Dr. Kempaller and Dr. Paul Reba. And since 2018, Laura is assistant professor in the Department of Psychology at the Western Institute for Neuroscience, Western University, Canada. Laura is interested in the neural basis of language acquisition, learning, and memory, sleep-dependent memory consolidation, conscious awareness, and many other aspects of cognition. I actually had the pleasure to meet Laura on a couple of occasions during my first year of PhD at the 2022 meeting of the Cognitive Neuroscience Society in San Francisco and in San Sebastian for the conference on interdisciplinary advances in statistical learning. So I also hope to see you there next month for another conference, another illuminated talk. Laura's research on statistical learning has been truly inspiring for my PhD. In particular, her work really stood out to me as she managed to unpack this phenomenon of statistical learning by looking at how primary neural mechanisms that reflect the sort of the process of learning might trigger then secondary long-term memory outcomes, and what's also the difference between implicit, explicit sort of learning there. So in today's talk, Laura will present a series of studies focusing mostly also on these aspects of statistical language learning. And without further ado, I would invite Laura to give her talk, and we are all very much looking forward to it. So the floor is yours.
Thank you so much, Lorenzo, for that really kind, nice introduction. And thank you so much for having me here to present. I'm really excited to share some of my work and hopefully have some discussion about it afterwards. So thanks very much. Okay, so we've probably all had this experience of listening to somebody speak in a completely unfamiliar language, which sounds just like a rapid fire, continuous stream of jumbled syllables with no coherent words that we can perceive. And clearly this is different from how we perceive a language that we know, a familiar known language, maybe our native language, which is as a sequence of discrete words with the perception of nice, clear separations between each word. So it's illustrated in these speech spectrograms here. I don't know if you can see my mouse, but the presence of pauses is a very unreliable marker of word boundaries in continuous speech. So sometimes you may have a silence or a pause within a word. At other points, you may have words that are sort of squished together without any pauses in between. So unlike in written language, where we have these nice demarcations between each word with spaces, in continuous speech, there are no reliable pauses in the signal to indicate where one word ends and the next begins. So if we're wanting to learn a completely unfamiliar language, maybe as babies, maybe as adults learning a second language, how is it that we're able to break into an unfamiliar language? How is it that we're able to take, for example, this continuous speech stream, in this case in English, and figure out where these pauses, where these words begin and end? So one way that it's thought that we're able to do that, there are likely to be multiple mechanisms, multiple cues that can help us do this. But one way is by becoming sensitive to the sound patterns within a spoken language. So taking this sentence as an example, there are no reliable silences between words. Someone who doesn't speak English would have no way of knowing whether there's a pause between no and re, for example, or re and lie. But across the English corpus, across the language, syllables on average that occur next to each other within a word, such as re-lie, tend to occur together more frequently than syllables that occur across word boundaries, such as no re in this example. So for example, we have the word rely, reliable, relies, reliance, reline. There's many words in English that contain this re-lie syllable. So this is a more frequent combination of sounds than no re. And if over time we're able to become sensitive to this idea, this fact that re-lie occurs together more frequently, this is one mechanism that may help us to break into this unfamiliar language and begin to pick up on a potential word boundary in this continuous speech stream. And this is known as statistical learning, first coined by Safran and colleagues in 1996 in infants and later shown in adults. And this is thought to be one mechanism that's able to solve this word segmentation problem or the speech segmentation problem. So in the laboratory, statistical learning is typically studied using an artificial language paradigm. Now, I don't remember if I shared my audio. Let me see here. I'm going to play this and maybe you'll hear it, maybe you won't. Maybe give me a thumbs up if you can hear it. So it sounds a little bit like this. Turn my speakers up. Oops. So I won't subject you to that for too long, but essentially there's this monotonic speech stream of continuous syllables. And initially it may just sound kind of like random syllables concatenated together without any spaces. But the idea is that over time, people may become sensitive to the fact that this speech stream is actually made up of component words, in this case, 4 hidden component words that are concatenated together without any spaces between each one. And then in adults, at least, the way that this has traditionally been assessed is by using a 2-alternative forced choice recognition task. So after the exposure period has been completed, participants are given on each trial this task where they're asked to discriminate between a word from the speech stream and a foil that's made up of recombined syllables from the stream. And if they correctly endorse the word from the speech stream, we infer that the statistical learning process has taken place if they're able to do this above chance. But many people have pointed out, including myself, that there are weaknesses to this task, including that it relies on explicit memory. And often it's not all that, performance on this task isn't all that impressive. It's around 60–65% or so in adults. So it may actually be underestimating or not very well characterizing this process of learning that we're really interested in. Another way that we can measure learning is through an indirect or implicit task where participants have the opportunity to express their knowledge of the statistical regularities in a way that doesn't ask them to make a direct judgment of what they've learned. So this is, we call this the target detection task, and essentially they're given a shorter snippet of the speech stream, and they're asked on each trial to detect a specific syllable. So for example, if they're asked to detect do in the speech stream, this is a word initial syllable. And so we expect that they're going to be relatively slower to detect this because they don't have any opportunity to anticipate the upcoming syllable. In contrast, if they're asked to detect a syllable that occurs in the third position, such as ba, we expect that this is going to be relatively faster because they're already listening to do ta, and they might be able to then predict ba more quickly and efficiently. And so this is indeed what we find across many studies. We've been able to show that participants are on average faster to respond to third syllable position targets in this task as compared to first syllable position targets. And in addition, what we've also found is that often people who may fail to show performance, above chance performance on the recognition task, are able to express their knowledge on this more implicit measure, the target detection task, suggesting that it may be a more robust measure of statistical learning. And finally, a variant on the two alternative forced choice explicit measure that we've begun to use often, which we call the rating task. So this is in some ways conceptually similar to the alternative forced recognition task, but on this task, participants are given items in isolation, and they're asked to rate on a 1 to 4 judgment how familiar that item sounds. So a word from the language should be given a higher rating in this case than a foil, than a non-word that's recombined from the language. So all of these measures basically assess statistical learning in a different way, but they're all assessed after this learning process has already occurred. And this is where neural entrainment comes in. So I think this is a topic that, that many of you are familiar with, so I won't go into a lot of background here. But essentially, the idea is that we can use neural entrainment as a way to measure statistical learning online during the learning process without asking participants to make a judgment on their own memory, or even without performing any task at all. And this is by measuring neural activity, such as with EEG, during exposure to the speech stream. So neural entrainment, in our case, will take advantage of the neural steady state response. So I like to show this study as a nice early example of the type of phenomenon I'm talking about here. So in this study, they had participants exposed to steady light, and then they flickered the light at 40 hertz. And in this case, what they saw over occipital sensors was the alpha rhythm diminished as soon as the flicker began, and then the oscillatory rate began to match the rate of the flicker frequency here. So this is the type of phenomenon I'm talking about. So here I'm really using neural entrainment in the broad sense rather than the narrow sense. And in our studies, we don't have direct evidence for certain assumptions being met, such as the presence of an ongoing oscillator that then aligns with the speech stream. So you could consider neural entrainment here as essentially a synonym for neural tracking, at least for the purposes of this talk. So essentially, by making a slight tweak to the stimulus design that I just presented, we can use neural entrainment to measure statistical learning as it occurs online. So here we present syllables at a steady rhythmic rate of 300 milliseconds each. And this will elicit a neural steady state response at the frequency of the syllable rate. You're at 3.3 hertz. But because neural entrainment is not just sensitive to low-level acoustic features of the signal, it's also been shown in many studies in music cognition, for example, that it can be sensitive to the subjective perceptions of stimulus as driven, for example, by top-down knowledge. So the idea is that as participants begin to pick up on the structure of the speech stream, we'll see a corresponding oscillatory frequency rate following at this word frequency, 1.1 hertz here. So as participants begin to become more sensitive to this, these words in the speech stream, we should see greater corresponding entrainment at the word rate and possibly reduced entrainment at the syllable rate as their perception shifts from being one dominated by the raw syllable baseline frequency to becoming more sensitive to the words. So we expect to see this change in time at neural entrainment between these two frequencies. And in addition, we may also expect there to be individual differences that we could capture with this measure. So somebody who's maybe a very good learner, sensitive to these rates, sensitive to this hidden structure, might show stronger neural entrainment at the word frequency. And in contrast, someone who's not as good of a learner might show relatively stronger neural entrainment at the syllable frequency. So these are some predictions that we had going into our first study, where we just wanted to see whether we could use this as a measure to assess learning. And just a note on the dependent measure that I'll be presenting throughout the talk is going to be intertrial phase coherence. So you can see typically similar things using a power-based analysis. So as I mentioned in the first study, we just tested whether this method of EEG-based neural entrainment could be used to assess statistical learning. So to do this, we had participants complete or be exposed essentially to two types of conditions. There was a random condition in which the syllables were presented in a pseudo-random order. And then we had a structured condition in which a separate group of syllables was presented according to this trisyllabic structure that I described earlier. And then after learning, we assessed their learning with two measures, the explicit rating task, as well as the implicit target detection task, as described earlier. So what we found here, here I'm plotting frequency on the horizontal axis and intertrial coherence or neural entrainment on the vertical axis. And what we can see in the structured condition shown here in red is we see this clear peak in neural entrainment at the word frequency, and this is not present in the random condition. We also see changes in these entrainment profiles over time. So by dividing the 12-minute exposure into 3 separate blocks, we can see that the word frequency shown in the structured condition, shown here in red, increased over time, whereas at the syllable frequency, this entrainment decreased over time. And in contrast, in the random condition, these entrainment changes were not observed. They were relatively steady or similar throughout the exposure period. And then we also found a correlation between the word learning index, which is the ratio of word frequency relative to syllable frequency, and participants' facilitation on the reaction time target detection task. So people who showed relatively stronger word entrainment showed faster responses to third syllable positions in the target detection task relative to first syllable targets. So in this study, we found that we can distinguish with neural entrainment between structured and random input. Neural entrainment seems to track learning over the course of exposure to structured input, increasing over time. And it also seems to be sensitive at least to one measure of individual differences in statistical learning. We did not find this correlation between our explicit measure and neural entrainment, only on the target detection task. So these results illustrate the feasibility of studying 2 conceptually different dissociable mechanisms that may contribute to statistical learning performance on our end of exposure tasks. So one is essentially this, what I would consider to be the core mechanism of statistical learning, which is this online moment-by-moment discovery and encoding of the units in time, over time. And then this may then lead to longer-term memory processes, the ability to segment these trisyllabic words and to form long-term memory representations of them, which then leads to performance on these offline memory tasks. Whereas neural entrainment may more directly reflect this online segmentation process. And I'll return a little bit more to this idea later in the talk, where I'll sort of flesh this out a little bit more after I present some more results. So now that we have this neural entrainment measure that seems to be sensitive to statistical learning, we can use this measure to ask additional questions about the learning process. So for example, does it occur automatically, or does it require attention to unfold? And what about its developmental profile? Does it occur similarly in infants and children and adults, or do we see changes across the developmental trajectory? So these are 2 questions we've been able to somewhat answer, at least with this measure so far. In the interest of time, I'm really just going to focus on the first question here for this talk. But if anyone has questions on the developmental work in the Q&A, I'm happy to go into more detail at that time. So the question here that we wanted to answer in this next study is whether neural entrainment to speech patterns occurs automatically. So if we expose participants to an auditory speech stream, but we impose some sort of attentional bottleneck or attentional manipulation, do we primarily see entrainment just to the syllables, or will we still see some level of entrainment to the words as well? How automatic is this entrainment mechanism? So to answer this, we used a visual 3-back task, which is this demanding visual task, where participants were exposed to these rather abstract kaleidoscope images, and they needed to make a judgment about whether each image was a match with the item that was presented 3 images ago. So in this case, they would say, like, yes, this was a match. And in this case, they would say, no, this was not a match. So this is quite a demanding task. It takes quite a bit of attention to perform well on this task. And we used a between subjects manipulation here, where half of the participants were told to fully attend to the speech stream and to ignore these images. They were still asked to passively view them, but they didn't have to perform a task on them. And the other half of participants were still presented with the speech stream, but they were told that they could ignore the speech stream, and they were told to fully engage in this visual 3-back task. So what we found here is that, not surprisingly, we see a reduction at the syllable level as a function of attention. So people that were paying attention to the visual 3-back task, the divided attention group, show a reduction in their entrainment response and their neural response to the syllable frequency. And this is basically a good manipulation check showing that the sensory processing of the input was reduced as a function of the attentional manipulation when attention is diverted elsewhere. But interestingly, we didn't see any significant difference, actually very similar performance, similar value, in our word entrainment measure. And this suggests that this moment-by-moment discovery of the patterns in the input was not affected by this, at least this particular attentional manipulation. On our reaction time-based task, the target detection task, which again was administered after the exposure period, participants in the divided attention group did show a reduction, showing better performance or faster performance to the more predictable 3rd syllable positions. But this performance, this facilitation was less than that seen in the full attention group. So the slope of their prediction essentially is stronger in the full attention group. And what this suggests is that memory processes were modulated by attention. So if you're fully attending to the speech stream, you're able to form better long-term memory of those regularities. And there's essentially a dissociation here between this moment-by-moment entrainment measure and their later performance on the target detection task. Overall, this suggests that, at least for this particular manipulation, this core process of detecting statistical regularities does not seem to require attention. And then finally, we also replicated our earlier findings showing this relationship between neural entrainment and later performance on the statistical learning measure of the target detection task between both of our groups, across participants in both groups. So statistical learning can occur while you're distracted. And in the next study, we wanted to see whether we could push this one step farther. So when you're distracted, you're obviously still awake. You're still processing input in a fully conscious manner. But what happens when you're completely asleep? Since another part of my work looks at sleep, which I won't talk as much about in this talk, this was kind of a nice way to sort of bridge these 2 research interests as well. So this work was led by my thesis student, Stephen Zhang. And what we did here is we had two orthogonal languages that we tried to make as opposite as possible across a number of different features. So one was the triplet language, which again is composed of these trisyllabic words, typical to most languages that have been used in this literature. And then we also composed an opposite language, which was presented with a lower pitch, for example. And it also had only bisyllabic words rather than trisyllabic words. And the reason that we wanted to do this is because we wanted to have the same memory task across participants. So half of participants were exposed to this triplet language during non-REM sleep while they slept in the lab with EEG, and the other half were exposed to this pair language. And then we were able, when they woke up, to compare their performance directly on the target detection task in the triplet language. So the idea here is that if they benefit from exposure to the language during sleep, we may expect to see facilitated performance on this measure in the triplet group as compared to the pair group as a between subjects comparison. And our other question was one about entrainment. So do we see word level entrainment in our EEG response while participants are sleeping and being exposed to the language during non-REM sleep? So here what I'm plotting is the intertrial phase coherence across all our participants who are exposed to both the trisyllabic and bisyllabic language during sleep. And what we see is a significant response at the syllable level, which is a good manipulation check. Again, it confirms that at least basic sensory level processing was occurring during sleep. But at the word frequency, we didn't see a significant effect overall across participants. However, what we did find was this interaction with language. So there was a significantly stronger response for people who had been exposed to the pair language as compared to the triplet language. So when we followed up on this interaction, what we found is that within the pair language, we actually did see this significant entrainment response to the bisyllabic words. So here you can see this peak as compared to our surrogate distribution at the word frequency in this group of participants, as well as at the syllable frequency. And so although this is somewhat unexpected that we would see entrainment at one language and not both, what we think is happening is that it's possible that the sleeping brain may be able to detect simple repeating pairs of syllables, but not more complex triplet regularities. And this could be due to the physiology of non-REM sleep, where we see these slow wave oscillations that unfold at about 1 per second. And this is made up of optimal and suboptimal cycles of oscillatory activity. So it's possible that two syllables can be bound together sort of within that optimal phase of the slow oscillation cycle. But once you get to tacking on more syllables, such as in the trisyllabic condition, at that point, the word length becomes too long to fit within that optimal cycle and therefore prevents binding together of that regularity. This is just a hypothesis. We didn't expect this necessarily when we set out to do the study, but this is one explanation for why we might see a pattern of results such as this. And then finally, we compared our participants' performance on the target detection task. And we found that both groups showed facilitation on this task, showing that they were able to learn as they were exposed to the language during the task itself, but the two groups didn't differ. So we don't have any evidence that being exposed to this language during sleep resulted in any long-term benefit as assessed on the target detection task. And so from a more practical point of view, this result suggests that exposure to a novel language during sleep may have limited practical value, at least for the type of speech processing and segmentation that we're looking at with this particular task. Okay. So I don't know if anyone had questions. I think there's someone. Did anyone have a question before I transition to the next study? Okay. All right, so the next study is a little bit more of a transition into really trying to understand more of the mechanism that's underlying neural entrainment in the context of statistical learning. So up until now, we've really been considering neural entrainment primarily as a measure of statistical learning, for example, reflecting the perceptual binding of syllables into integrated units, and showing a correlation between stronger entrainment corresponding to better performance on the target detection task, for example. But we haven't really gotten into what the exact relationship is between entrainment and statistical learning. So here we're really testing between two possible theoretical possibilities. So one is that entrainment is reflecting the downstream consequences of the statistical learning process itself, such as the enhanced perception of individual words in the speech stream. So here, for example, it may be that there's something else driving the learning process, and that entrainment is picking up on the outcome of the learning process while individuals are listening to the speech stream. But the other possibility is that entrainment may actually be playing a causal or functional role in the statistical learning process. And this possibility is supported by different frameworks for neural oscillations and stimulus processing. So for example, models that suggest that information that arrives at a low excitability phase of a neural oscillation is processed less efficiently, while stimuli that arrive at a higher excitability phase of a neural oscillation are processed more efficiently. So the phase at which the stimulus arrives with respect to an ongoing oscillation may have outcomes for how that stimulus is processed and the efficiency for which that stimulus is processed. So if we kind of extend this framework to statistical learning, we might expect that by aligning peaks of neural excitability with the hidden word structure, this could potentially facilitate processing at key moments of the speech signal, for example, at the word onsets. And this thereby could lead to enhanced perception of the component words. So in this case, by aligning neural oscillatory patterns to the hidden word structure, we may help transition learners' perception from individual syllables to whole word units. But in contrast, if we had an oscillatory frequency that was misaligned with the component words or out of phase, for example, then we might have the optimal phase occurring at any moment of the speech signal. And it might occur sometimes at the beginning, sometimes at the middle, sometimes at the end. And overall, this could actually interfere possibly with statistical learning by having high excitability phases coincide with non-optimal moments of the speech signal. So this is kind of the theoretical idea that we're trying to test with this next study. And the possibility of a causal role in entrainment in statistical learning is also strengthened by other studies, including some work done here, or where you are, rather, not here, but where you are, which has shown that neural entrainment causally influences speech perception. So it's not too much of a stretch to think that there might be some role in statistical learning of speech. So to test this question, we used a visual stimulus to induce specific neural entrainment frequencies during the learning process. So what we did is we had participants listen to our speech stream as they normally do, but then they also watched a visual, circular or rhythmic visual movie that showed a water droplet falling off a leaf and landing into a pool of water below. And by adjusting the speed of this video, we had this cycle either occur at the same frequency as the trisyllabic word structure, at a faster frequency than the trisyllabic word structure. And then in a third condition, we had just a static image. And participants weren't told about the congruency or incongruency of the visual manipulation with respect to the auditory speech stream. We told them that we kind of misinformed them about this, and we told them that it's just to look at whether watching a relaxing nature imagery can help them pick or help them learn and process speech. So they weren't told about this. And most of the participants, or almost all of the participants that we interviewed after, didn't seem to pick up on this relationship. So we've had 20 participants per group. And then they did our rating task and our target detection task. So the groups differed during the exposure period, but during these tasks, the tasks that were followed after the exposure period were exactly the same between the groups. And this work was part of Jericho Mulgrew's thesis work, so I wanted to acknowledge her efforts on this project. So I will play the little snippet of the video and the speech stream just so you can kind of get a sense of how this was for the participants. Hopefully the audio comes through. I won't play that for too long, but that was an example of a congruent condition. So the water droplet is at the same oscillatory rate or at the same rate as the underlying words in the speech stream. So moving on to the results, here we examine neural entrainment specifically within an auditory region of interest where auditory entrainment was maximal in the static group. And what we see here is this in the congruent group shown here in turquoise, we see this large boost in entrainment at the word frequency. And we had to do some steps to make sure that this isn't just a result of passive volume conduction coming from occipital regions. So we applied the logic that's used in the cross-modal field And we found evidence that this was a super additive response. So in other words, it exceeded the response that was estimated based on only the speech stream alone and only the visual stimulus alone, which suggests that it's engaging some of the same neural oscillators, or the same neural substrates at least, that were initially used to process the speech stream. And then this gives you a little bit of an idea of the distribution of the effect. So what you can see in the congruent condition when it's plotted at this scale here is that it's this really massive widespread entrainment effect. So when we rescale this, what we see is that there's a lot of entrainment happening at occipital regions over the posterior part of the scalp, which is not surprising given it's a visual manipulation. But we also see some effects here that are larger sort of over frontal central regions. And this was a Laplacian filter. So we're able to sort of separate out these two sources here. And again, this is at 0.6 maximum ITC. So we see that this is much larger in the congruent group as compared to the incongruent and static group. So based on this, we think that this visual stimulation did successfully boost neural entrainment within our auditory electrode region of interest. So then we moved on to the target detection task. So just to recall, at this point in the procedure, the tasks themselves are identical between the three groups of participants. So there's no differences in the physical stimuli at this point between the groups. They're all just doing the target detection task without any visual stimulation. And what we see here is that the congruent group had been exposed to the trisyllabic structure on top of the, with a congruent visual stimulus, shows a significantly enhanced reaction time for the more predictable targets that occur in the third position. And when we look at entrainment over the target detection task, so the neural response to the speech streams that are presented during this task, we see something kind of converging at the neural level, which is that the congruent group shown in turquoise again is again showing this stronger word level entrainment response compared to the other two groups. Now, we don't see any differences between the incongruent groups and the static groups, suggesting that the misalignment of the visual stimulus did not impede learning. It's just that the adding to that effect with a visual stimulus seems to slightly enhance statistical learning. So these results suggest that by manipulating neural entrainment during exposure to the regularities, we can influence statistical learning outcomes, which suggests that neural entrainment may functionally contribute to statistical learning. So this is just one study, and we're currently following this up using a transcranial alternating current stimulation to see whether we might get converging evidence through non-invasive brain stimulation by manipulating frequencies that will either align or misalign with the words in the speech stream. So I'm going to just talk about one final study now before getting to some general conclusions. And in this study, we're starting to examine, using neural entrainment, which brain regions may participate in the statistical learning process. So as you likely know, the one limitation of scalp EEG, which I've been talking about up until now, is that it really doesn't have very good spatial resolution, and it doesn't really allow for pinpointing which regions of the brain may participate in the statistical learning process. In contrast, intracranial EEG, or stereotaxic EEG, provides both temporal and spatial precision. So this is conducted in patients who are being treated surgically for drug intractable epilepsy. And they have a surgery that basically has their, where the surgeon goes in and implants electrodes into their brain in different regions. And this is done to localize the seizure onset zone and plan their treatment. And so many of these patients are gracious enough to allow us to conduct studies while they're in the epilepsy monitoring unit being monitored for epilepsy. And this gives us a unique opportunity to look at where some of these signals, where in the brain entrainment is occurring during exposure to the speech stream. This work is led by my graduate student, Daniela Herrera Chavez. So just going backing up a little bit here. So what we do know about previous evidence on the neural regions supporting statistical learning largely comes from fMRI work. And this work has mostly been carried out in the visual domain with relatively limited work on the neural basis of statistical learning as it occurs during speech processing. So from what we do know from fMRI mainly is that during statistical learning, we see greater activation to structured patterns as compared to random patterns across different regions of the brain, mainly involving two main categories, I would say, including sensory regions as well as frontal regions. And the hippocampus here is of particular interest. Some fMRI work has pinpointed the hippocampus as potentially being involved in statistical learning. And in addition, a recent computational model by Shapiro and colleagues suggests that the two pathways of the hippocampus may differentially support statistical learning and pattern separation. So pattern separation may be supported by the trisynaptic pathway of the hippocampus, whereas statistical learning may be supported by the monosynaptic pathway of the hippocampus. And so this is a really interesting idea that the hippocampus may be supporting both episodic learning as well as statistical learning through this division of labor. But there's limited direct neural evidence of this idea in humans. So we wanted to examine whether we could see some of these same regions implicated through our neural entrainment paradigm and in the context of speech segmentation rather than visual statistical learning. So returning to the intracranial EEG, I'm going to present here data from 13 patients who had drug-resistant epilepsy and who underwent SEEG for seizure investigation. And these patients were all recorded from the epilepsy monitoring unit at University Hospital in London, Ontario. So you can see their demographic information here, most of them being within in their 20s and 30s, with a few younger and older. And this is an ongoing line of work, so I'll just be presenting some preliminary data today. So this is the protocol that we give everybody in the same order, which is not counterbalanced. And this is so that we can try to get as consistent of results as possible across our patients. So it looks quite similar to the protocol that I've presented in earlier studies. They get exposed to the structured artificial language. They then complete the target detection task, again, with reference to the structured language. Then they do a familiarity rating task as an explicit measure of their learning. And finally, as a control condition, they get exposed to a random artificial language where the syllables are randomly concatenated together. Okay, so moving on to our behavioral results that we have so far with our 13 patients. On the target detection task, we found that most patients showed evidence of learning as indicated by faster response times to the third syllable target as compared to the first syllable target. So 11 of the 13 patients showed this profile, and only 2 of the 13 patients did not show that type of learning curve. And on the familiarity rating task as a group, we do see that words are rated slightly more familiar than non-words. But we see a lot more heterogeneity in this effect across our patients. So only 6 of the 13 patients here are showing evidence of explicit knowledge on this rating task. Actually, the majority, slightly more than half, do not show stronger or higher ratings for words as compared to non-words. So we might conclude that the target detection task is a more robust measure in this group of patients, that overall patients are tending to show learning more robustly on the target detection task as compared to the familiarity rating task. So moving on to the IEEG results. So this is the entrainment profile that we see across all sensors, collapsed across all of our contacts and patients. And the structured condition here is shown in pink and the random in blue. And we see a fairly similar profile actually to what we see with scalp EEG, which is that we see a larger entrainment response in the structured condition as compared to the random, and then a very similar effect at the syllable frequency. And one thing that we can't do with scalp EEG, of course, is look at where in the brain those individual responses are coming from. And when we look at the sensor level, what we see is essentially 3 profiles of neural entrainment that emerge. So there are some sensors that show entrainment only at the word frequency. And this is assessed using a surrogate distribution where we shuffle the data with respect to the auditory speech stream. So we misalign that with 1,000 surrogate data sets. And then we assess whether the response that we're seeing exceeds that 95th percentile after FDR correction. So we see these 3 profiles, a stronger, some sensors entrain to the word frequency alone, some show entrainment to the word and syllable frequency. And then finally, we have a 3rd group that doesn't show any word entrainment, is only entraining to the syllable frequency. This gives you a little bit of an idea of where these 3 different profiles are occurring within the brain. So what we can see is surprisingly that there's much more entrainment to the word frequency in the structured condition. A large amount of electrodes are showing entrainment to the syllables, about 40% overall, and about 18% of electrodes are showing entrainment at the word frequency. Within the word frequency, what we can see is that the main regions that show entrainment occur in the superior temporal gyrus, the medial temporal gyrus, and the insula, as well as the putamen within the parietal lobe and within the frontal lobe. And the entrainment effects in the hippocampus were actually very limited in contrast to our hypothesis. We found only 3 out of 118 electrodes within the hippocampus, so less than 3%, showed significant entrainment within the structured condition. So these results implicate this widespread and robust network showing entrainment throughout auditory association regions, in addition to the insula, frontal and parietal regions, and the putamen. But we did not find convincing evidence of hippocampal involvement in statistical learning. So again, this is ongoing work. We're still collecting data from more patients. But the idea that there's so far no convincing evidence that the hippocampus is part of this network in our data set, at least, raises to us at least 2 possible interpretations. One is that perhaps statistical learning of this nature doesn't actually require or engage the hippocampus. So this would be in contrast to the predictions of Shapiro's model. The second possibility is that maybe it is engaging the hippocampus, but not through entrainment as a mechanism. So entrainment may not be the way to really characterize this involvement. And we're following up on this by using some different types of analysis approaches to get at this idea, to test whether there might be evidence of hippocampal involvement when we use something like a pattern classification analysis. But to date, this is the story that's emerging so far. Okay, so just to conclude, kind of give you some take-home messages from what I presented today. How do all these results fit together? So to summarize what I've showed you, neural entrainment across studies reflects statistical learning. We see that it increases across exposure to the regularities in our time course-based analysis and predicts subsequent performance on the target detection task. We see that it can occur outside of focused attention, and at least for very simple regularities, even during sleep, suggesting that it's a relatively automatic phenomenon. And there's initial evidence from our one study that it may not only reflect, but actually functionally contribute to statistical learning, so that it's representing not just a measure of statistical learning, but also an underlying mechanism. And finally, with the last study I presented, we're seeing entrainment across a widespread network that's engaged during the statistical learning process, including auditory regions, the insula, and frontal and parietal regions. But so far, no convincing evidence in the hippocampus. So I'm going to conclude by presenting sort of a working hypothesis or a conceptual framework that we can use to then motivate further work in this area and make predictions about the underlying mechanisms that may be occurring. So with the results so far, we might propose this following kind of perceptual or working hypothesis framework. So in this example, if a repeated pattern is presented to the brain, shown here as pattern ABC, we can propose that learning this type of pattern is supported by this kind of core pattern discovery mechanism that's relatively automatic, and that can be captured by neural entrainment. Depending on the type of learning, these changes in the brain may be transient, or they may dissipate rapidly or be stabilized. And with stabilization, this could be sufficient to support some behavioral expressions of learning, for example, as shown by being able to make predictions to predictable syllables as measured by the target detection task. In addition, exposure to the input may optionally, but not always lead to secondary memory processes, potentially mediated by the hippocampus, which can then allow for the flexible relational processing of memory. And this might be expressed through something like the rating task. And this can support the ability to make explicit judgments about the regularities, but doesn't necessarily always occur when the brain is exposed to regularities. So roughly, this could map onto what we know about declarative and non-declarative, or explicit versus implicit memory, with this core mechanism being largely implicit or automatic, and this secondary relational processing being more explicit or declarative in nature. So these perceptual patterns, just to summarize, may be occurring almost as a near-obligatory response to structure encountered in the environment, occurring without requiring effort or intention to learn, and then may optionally, but not always, lead to the formation of long-term memory. I showed you evidence today about its automaticity, that occurs during sleep, that it may actually play a functional role in learning, and that it may occur throughout a widespread, robust network in the brain. And though we didn't have time to get into the evidence in this talk, we also see that this entrainment mechanism is very similar and consistent and robust throughout development. And in contrast, we think that this ability to explicitly discriminate between learned items may be one of the more vulnerable aspects of performance of statistical learning. So in our SEEG patients, we only see about half that are able to do this task. And we also have evidence from older adults, as well as a patient with a selective lesion to the dentate gyrus, that they're able to do the implicit task for statistical learning without any impairment, but they are impaired on this rating task. Okay, so that basically wraps up what I wanted to present. Just to acknowledge all the collaborators on both the EEG work as well as the intracranial work that I presented today. My sources of funding. I also wanted to mention that I have 2 postdoctoral positions that are going to be opening up soon, as well as a position for a sleep technician and a project manager for a newly funded 3-year project looking at phase-locked auditory stimulation, sleep, and memory. And thank you for your attention. I'd be happy to take any questions.
Thank you very much, Laura, for the wonderful presentation. We have now time for questions. So we don't have a room today, so everybody can post questions in the chat or just raise your hands. We have a question already in the chat, a couple of them. So Luisa Bogarts, if you want to ask your questions, maybe Caro, you can unmute. Otherwise, I can read the question myself.
Should I stop sharing my screen or keep sharing?
Yeah, you can keep sharing.
Okay.
Yes, now I could unmute. Really interesting talk, Laura. So I just wanted to ask about the idea of entrainment also being a discovery mechanism. How that would work in real language, because of course syllables would be combined not always in pairs or triplets, but could have different lengths. And so you wouldn't have one exact frequency that nicely matches on the signal. And so I was just wondering to what extent this would kind of be useful outside of the very controlled lab setting where you're always doing triplets or pairs.
Yeah, that's a great question. So I think it can still, given what we know from the oscillatory literature that accounts for speech perception, We know that there are different oscillatory frequencies that sort of align at the syllabic rate, for example, at the word rate, at the phrasal rate. And these aren't going to be perfectly fixed like they are in this artificial language study. But I think that the overall framework could still apply here, because I don't think it's a necessity that it's fixed to have this effect. But you could imagine, so for example, there have been studies that have modulated the brain at the rate of the speech envelope, and shown using transcranial alternating current stimulation TACs, and shown that that impacts the ability of people to comprehend speech. So that's not going to be like this very fixed artificial rate of entrainment. It kind of it follows the amplitude of the speech envelope, so it's going to be somewhat variable. So I think by extension, we might expect that even if there is not a perfectly fixed oscillatory frequency with which our words are presented, which of course would never be the case in a natural language, we might still expect that by modulating those frequencies, we could have an impact on how that learning occurs, and possibly by increasing the entrainment at the underlying word units, even if those aren't fixed in completely fixed or completely stable in frequency, we may still be able to facilitate that learning process. But I think this is still very early days, so we need to do a lot more work that doesn't rely on a sensory manipulation to really understand fully if that's going to be the case. So, Louisa, did that answer your question?
Louisa still reply? Yeah. I would assume it did for now.
She said yes.
Oh, great.
Okay.
Next we have Philip. If you want to answer your question, ask your question.
Yes, thank you. Thank you so much for the very interesting talk. My question is about the timing of the maximum synchronization between the stimuli and the neural signal. If it's changing when the participants are learning the statistical regularities, I would expect it would be faster. Maybe the synchronization could happen faster when they learn the statistical regularities. I wonder if you also maybe compared the phase difference between the stimuli and the neural signal at the beginning and at the end of the statistical learning task.
Okay, so if I understand your question, are you asking whether the neural oscillatory entrainment that we see changes over the course of learning, or are you asking more about whether the preferred phase changes over the course of learning?
Yeah, the preferred phase throughout the learning.
Oh, okay. Yeah, with our measure of intertrial phase coherence, we don't know anything about the preferred phase. So we could look with the data we have, we could look at that. But as of now, we haven't looked at all at whether, you know, the phase differs over the course of learning. So I can't speak to that directly, but that's an interesting idea. I guess there is some literature from other domains that suggests the phase may sort of shift, but as of now, yeah, well, that isn't something we have looked at.
Okay, yeah, thank you.
Yes, thank you. Next we have Jeremy.
Yeah, thank you. Hello. Thank you very much for the talk. This is very enlightening. I was wondering, since these results are based mainly on Professor Safran's original paradigm, I was wondering how these results might mean for other paradigms of statistical learning, like distributional learning by May, unimodal bimodal exposure, or cross-situational word learning by Smith, and so on. Thank you.
Yeah, that's a great question. So I think the type of entrainment we're looking at here really is kind of the binding of syllables together as they occur across time. But I think there might be sort of more broad extension that could be made for something like distributional word learning, cross-situational word learning, if we think that that item will also be represented by some sort of neuronal assembly. And if it co-occurs at the same time as this unit of speech, that could then form this link that then could also produce some kind of rhythmic response were it to be presented rhythmically. I think the entrainment response is essentially reflecting two or more units that are active at the same time and then become strengthened through some sort of Hebbian learning process that would be quite automatic. So I think the same thing may apply more or less to depending on the type of learning that occurs. And if it's a sort of cross-situational word learning, it may require more attention than the type of learning we're looking at here, but you may still see some sort of similar mechanism. So I think it's still quite an open question, and we don't have too much evidence as to how that would be affected by sort of the presence of an item, for example, that's consistent across time.
Thank you very much.
I have a question. Thank you for your talk. I wondered if you had thought about subjective rhythmization ability, because your participants are exposed to this monotonous train of syllables. And we know from work with metronome, for example, is that participants differ in their ability to impose structure on unstructured rhythmic signals like metronome beats, or in this case, syllables. Do you think this subjective rhythmization ability plays a role? Because some people naturally would, rhythmicize at group of 3 level. Some people would rhythmicize at larger or smaller chunks. Do you think this subjective rhythmization ability plays a role in the task?
Yeah, that's really interesting. I think it definitely could. We don't have direct evidence in our task, but it reminds me a bit, your question reminds me a bit of the spontaneous speech synchronization task that has been conducted before. So it's like Asanio, I think, is the main author on that paradigm. So essentially just whether participants are able to, or whether they spontaneously synchronize their own speech to sort of this ta, ta, ta whisper. So they're presented, I think, in one ear, this whisper that's just ta, 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 and about half of the population spontaneously synchronizes and half of the population doesn't, according to that line of work. And that has also been shown that the people who do spontaneously synchronize seem to do better at this type of Safran statistical learning task. So I think by extension, it would be reasonable to think that those individuals who are more spontaneous synchronizers may show higher entrainment, for example, in our statistical learning task. That is something we are assessing right now in a collaboration. So we don't have the results yet, but I guess that somewhat gets at your question. But the other part of your question, I think, is whether there are individual differences in sort of people's natural group that they prefer to chunk at. And yeah, I think that could for sure influence how people are approaching this task, maybe the rate at which they're performing this task. I think it's basically like a very reasonable hypothesis, but we just don't have any actual data to say either way yet. But thanks for the question. It's really interesting to think about that for future work.
Hi, thank you. This is really cool work. I was wondering if you could just talk a little bit about entrainment if you think it's a unitary mechanism, or might it also reflect multiple mechanisms that, have traditionally or have sometimes been argued to be distinct, for example, striatal-based learning, cortical learning, or you talked a little bit about hippocampal learning. It seemed like you were talking a little bit towards the end about mechanisms in the plural, but I just wonder like what your thoughts are on that.
Yeah, so I think with our last intracranial EEG study, we do see that entrainment can come from a wide variety of different brain regions. So the putamen, we saw some participation in the entrainment there, mostly medial and superior temporal gyrus, so implying that it's probably quite a sensory-driven process. But then also what you would consider to be sort of like higher level, broadly speaking, regions like within parietal and frontal lobe. So I think it's a mechanism that could engage many different brain regions. In that respect, it's almost interesting that we did see so little of that in the hippocampus, sort of suggesting that the hippocampus may be doing something quite different from what these other regions are doing during statistical learning. There's, I mentioned Shapiro's model, but fMRI work shows that in a lot of these visual statistical learning paradigms, you see engagement of the hippocampus. So it may be doing something kind of more divorced from the stimuli itself, if I could say that. So it's maybe something that's a bit more of an abstraction compared to an entrainment type of mechanism. But I think, yeah, there's a lot that we still don't know about exactly what that would be, especially in the context of speech segmentation. There's a paper that looked at, kind of did a similar paradigm in both the visual and auditory modality, and found that the hippocampus was sensitive to the units in both vision and audition, but not through an entrainment mechanism, kind of through a pattern similarity based analysis. So again, that's quite an abstract way to look at what the hippocampus is doing. It doesn't seem to be entraining to the regularities in the same way that a lot of other regions that we have do. And we also have a lot of coverage in the hippocampus compared to other regions too. So we can't say that it's kind of a sparsity issue. We have every patient had electrodes planted in the hippocampus compared to frontal and parietal regions, which were much more sparse. So
very cool. Thank you.
thanks for the question.
Thanks for the questions. I think we can close with a couple of questions from Lars. We still have time for that. So Lars.
Great. Thank you for the presentation. I have so many questions, but I'll restrict myself to 2 questions. The first one is, and that was kind of fascinating, the one, well, many things were fascinating here, but the one with the water drops, that was kind of cool. So I was wondering whether you could speculate a bit more what exactly is going on. I mean, what does the dropping water have to do with the auditory system? Why would it like sharpen the response or like lead to either stronger entrainment or a sharpened early negativity complex? Like what's happening there on a cognitive level?
Yeah, so I think that's basically a cross-modal kind of effect. So I guess humans are very visual creatures, and so we have this rhythmic visual stimulation that's clearly capturing a large amount of visual cortex, and some of that activity will start to will influence at least cross-modal networks that are active in both audition and vision. I also think it's interesting to think about kind of phenomenon like the McGurk effect here. So we know that vision plays a role in our ability to perceive speech. So it may be that there's, and this happens without people, strategically being aware of these cross-modal influences. So we know that there are mechanisms that allow us to be sensitive to visual input in addition to auditory input, and that if there's a synchronization between vision and audition, there's mechanisms in the brain that are sensitive to that and that can influence our speech perception at least. So I think something similar could be happening here, where we're basically driving the visual system in a very strong way, and some of that visual entrainment is having an influence on the same neuronal networks that are involved in statistical learning. So it's not that people think that the droplet of water has any relevance per se to the speech segmentation, but there's this kind of coincidence that occurs between the two streams of information that's then kind of driving at least a subset of the neurons that are active in the speech processing to have this stronger response at the relevant frequency.
Yeah, so it's, I mean, like what you say sounds like it's more about just like directing the attention in time, right? So like, but I was more trying to get at, would it make a difference, say, if the visual stimulus produces a sound? You just don't hear it, but you see something that produces a sound, and you see it at the same rate as the auditory relevant stimulus, and then you present something, a visual stimulus that doesn't make a sound. Would that make a difference?
So if I understand your question, you would have the same speech stream, or is this a completely different paradigm?
Yeah, same speech stream, and then you present a visual stimulus that produces, well, that in principle produces a sound, but you don't play the sound. You just show something that produces a sound, like, I don't know, a mouth opening or a horn honking or something like that. So that you know that there's a sound occurring with the same period as your auditory stream. You just don't hear it. And would it make a difference compared to a visual stimulus that does not produce a sound?
Oh, that's interesting. Yeah. You would expect, if anything, it should be kind of a stronger entrainment response because your brain's expecting this sound. And yeah, that's a really interesting idea. Yeah, I mean, like the droplet of water is kind of ambiguous. Like sometimes it would produce a small sound, but it wouldn't be.
Exactly. That's what I was wondering about. Yeah, plop,
Yeah.
plop. But most of the time you don't hear it, right? Because it's too far away and too tiny.
Yeah. So I don't know. I think, yeah, we have sort of like one case on that is like could produce a small sound. You wouldn't be surprised to see that happening and not hear a sound either. So if you had something kind of analogous but that would be like a ball bouncing or something like that would typically produce a sound. Yeah. Then it would be
associate the content level from like the temporal attention level or the attention level in general. I think that might be a smart way of kind of pitting that against each other.
Yeah.
Thank you. And the second question I had was about the pairs in sleep study, where you had the triplets when people woke up and then you didn't see a difference. Can you show that slide again, please?
Yeah. Oops. So I just have to find the slide. Here we go.
Exactly. And now I was wondering, you didn't cross the task with triplet versus pair. So you didn't have a second group where you had like, you did?
So maybe I don't, this was the task that would occur for everybody right after sleeping, after the nap. Then we did also do a pair detection task after, and we also didn't find differences on that. But we also we don't consider that to be a very good measure because at this point they've already listened to the target detection task, and so there could be interference, etc. So we sort of designed it that this is the main dependent behavioral measure that everybody gets, that's like the least contaminated measure after the nap.
Yes. How, and sorry, it's a third question. I'm sorry, I didn't tell the truth. Anyway, I'll ask the third question. Would that be the same in say infants, or maybe you do have data on that?
You mean, would the infants learn anything during sleep? So we don't, but other studies have looked at this in newborns in training to statistical learning in speech. And they found, I believe, like a ERP difference in the infants when they're exposed to speech. So it may be that the boundary between wake and sleep is more fuzzy in newborns, and maybe the sleep is somewhat different for them in terms of like what they're processing, because they spend so much more of their time asleep. Or it may just be that, you know, these are two very different measures as well. So the target detection task is like, do you have this behavioral facilitation that depends to some extent on your long-term memory ability for the regularities? The ERPs in principle would also depend on some kind of long-term memory formation, but it doesn't rely on behavior specifically. So I guess it's quite difficult to disentangle whether we would get, you know, if an infant were able to do this task, would they show anything different? That'd be interesting, but obviously can't do that particular task in infants. So yeah, it's unclear, I guess, whether it's like the measure, if we could do ERPs here too and see whether we got something similar as the infant work. I guess that would be the way to go, rather than make an infant detect targets, which I don't think they're going to do.
Okay. Thank you so much.
Thank you.
All right. So I don't see any further questions. So with that, I would like to thank again our speaker of the day, Laura Batterink. Thank you very much. It's a really exciting discussion.
Thanks very much for all the questions as well, and the great things to think about for future work. Really enjoyed presenting here.
Great. Thank you. Thank you again. And see you everyone in a month, in June 12, for another meeting of the Language Circle. Good evening. Bye.
Thank you, Laura. See you in a couple of minutes, right?
Sounds good. Yes. See you soon.
Thank you so much.
Bye. Thank you.